So in this video, we will be writing, explaining, and testing a code to calculate the friction factor, head drop given flow, and flow given head drop for a pipe segment. So to start off, as you can see on the board, I have Bernoulli's equation divided by the gravitational acceleration. And again, in this situation, to start out, it did tell us that we will have a given flow, and that means that our velocity will be staying constant, so this term will just disappear. I'm going to get this marker to work nicer. So now that means that our velocity will be staying constant since our flow is staying constant. And now you can see I've written the right hand side of this equation here, and this is actually from a previous video where we calculated the fanning friction factor at laminar flow. And so as you can see, again, our pipe will be at a constant velocity and a constant diameter. So again, we got rid of this portion of the equation. So now you can tell that there is that velocity that we're going to have to find once we start coding. And then our cross-sectional area, the length of the pipe, and then here's our friction factor right here. So again, this is going to be the first equation that we're going to input into our Python code, and it's going to end up spitting out an answer in meters, which will end up being our head drop at a given flow. So many people have made equations relating Reynolds number and surface roughness to the friction factor. And right here is some of those equations, and the one that we will be using for our Python code will be the Churchill equation right here. But as you can see, it is divided by 8, but this is actually for the Darcy friction factor, and we will be using the fanning friction factor. So we are going to end up multiplying this all by 2 to account for it being our fanning friction factor, which is actually 4 times the Darcy friction factor. So to start off, we're going to make a function, or define a function for this Churchill equation. As you can see, I've already imported numpy as np. And then now we can define a function called Churchill. I'm just going to call it ch. And we're going to be inputting the Reynolds number and then our E over D here, which I'm just going to call ED. And colon there. And then first I'm going to put in this theta 1 equation, and then we will be putting in our theta 2 equation, and then our output will be this final Churchill equation. So theta 1 negative 2.457 times numpy log 7 over our Reynolds number to the 0.9. And then that plus 0.27 times ED. Plus and then now this whole thing needs to be to the 16th power. To the 16th power. Now we can do our theta 2. Which will just be 37,530 over Reynolds number all to the 16th power. Then we will be returning this here, again, times 2. So 2 times 8 over Reynolds number to the 12th. Plus 1 over theta 1 plus theta 2 to the 1.5. I'm just going to put decimals after all these numbers here, just to make sure it doesn't mess up. I always forget to do that. Theta 1, theta 2 to the 1.5. Okay. All that to the 1 over 12 times okay, so that should be the Churchill equation as a function in Python. So now we're going to actually start solving our problem, and we will need to define our function for the head drop now, and we will be inputting the flow Q, length of the pipe L, and diameter of the pipe D. And again, we're going to be using those right-hand side equations that I wrote on the whiteboard earlier. So we're actually going to need to define I'm going to add a line of code here. We're going to need to define our density rho, and since we're just going to say it's water, so 1e to the third, and then we're going to need the viscosity mu, which is going to be 1e to the negative third, and then we also need our gravitational acceleration 9.81 as well. So now we are going to need to define all those variables that I had circled on the right hand side of that equation, because once we get those values, we'll be able to set it equal to the left-hand side of that equation. So first we're going to do the velocity defined at a certain flow rate. So it'll be 4 times Q over pi d squared, our diameter. So numpy pi times d squared. And I'm just going to run all right now before we forget to define these variables and everything. And we also need the friction factor, F, which we can just use our Churchill equation here that we just saw. So Churchill, RE, Reynolds number, and ED, our roughness. And then we will also need to find our Reynolds number, which will be rho times D times V all over mu. And then we will also need our head drop function here to take in our surface roughness as well, since we will be using our Churchill equation again. And now finally we can return the equation that we had on the board, 2 times L times F times our V squared, and then all of that over our D times G. So let's first just make sure that this head drop function works. So we're just going to try to get a flow rate of 0.1. We'll say that the length of the pipe is 10, diameter we'll say 0.1, and the roughness 5e to the negative third. And as you can see here, we get a head drop of about 25.18 meters in these conditions here. So now we can start the final part of this problem, which will be calculating the flow rate when we know our head drop. So I'm going to define a function for the flow rate, define a function for the flow rate, and for this we will be inputting the head drop that we know, which I'm just going to end up calling beta, and then we will have the length, the diameter again, and our roughness again. And now we're going to want to define the equation that we are eventually going to be using our SciPy root solver on, since we will be solving a nonlinear equation. So for that equation, we are going to want one value in a vector x, and we just want the first value in that vector to equal our flow rate Q. And let's make sure that we have our colon there as well. And now what we will want to return in this equation will be a difference in these head drops. And we will want to know when they equal 0, and that will be the flow rate that we want. So we're going to want to return the difference between beta and then our head drop equation. So I'm putting Q, L, D, and ED. And using our SciPy root solver, we want this to be an array as well. Now with using our SciPy root solver, we will need an initial guess for our flow rate, and that's what we're going to solve an equation for right now. So to start off, we do know that we have our head drop beta that we know, and that will be equal to the opposite of the right hand side of this Brimlow's equation here, the negative G. And then again, we can input this equation from before, in here, and in here. But again, the head drop will be the opposite, so it won't be negative. So we can put it in here, beta is equal to 4 F delta X over dg v squared over 2. And then now we can eliminate this, or cancel out these 4 and 2, and just make it 2 F times delta X over dg times v squared. So now we can try to isolate v on its own side, so we'll multiply by dg on both sides. We get v dg, and then divide by friction factor times delta x, and take the square root of the whole thing. And then now what we can do is multiply by our cross-sectional area, pi d squared over 4, and then this will end up equaling our flow rate at giving gravitational acceleration qg, and this will end up being our guess once we start using our SciPy root solver. So now we can start plugging all this into our Python code here. So I'm first going to type in we're going to call this qguess. And so it'll be numpy pi times d squared over 4. All that times numpy square root of beta times d times g over, and this is where we will need an F guess as well. F guess, and we're just going to put that as 0.001 0.01. It's a really low range of values that our friction factor could be. So again, we're going to call that F our F guess, and then times our length. And then we will want to return using our root solver of the equation and using our guess value of Q guess and then we have to put that it is going to be our first value in our array. And then we have to again get our root solver. So from scipy.optimize import root. And I'm just going to run all. So now what we can do finally is just test to make sure that our function works. So we are going to use this head drop here that we calculated from before as our beta, and then we're going to use the same length, same diameter, 10, and then the same roughness. So this should be actually 10, and then 0.1, and 3, or 5e to the negative 3. And when I run this, it should give us about 0.01 that we had here for the flow rate.